Hi, everybody. My name is Anna Carroll, and as we just said, I'm going to talk about differential testing with Foundry today. Oh, okay. Yeah, so just to begin with a little bit of background, for people who don't have context, differential testing is a test method that's used to ensure identical behavior between two or more implementations of equivalent code. So in differential testing, you're going to take two instances of code that you expect to behave equivalently. You're going to test them by providing the same test inputs, and then you're going to ensure that all meaningful behavior of the execution is identical. That could just mean checking outputs, but it could also mean checking richer execution traces. It's good to note that in general, when people talk about differential testing, it's kind of loosely assumed that the inputs are generated or fuzzed. This is not a requirement, but it's kind of the general flavor of a lot of differential testing. So intuitively, differential testing is basically just this meme. You're just checking that the two Spider-Mans are the same. So differential testing for smart contracts specifically, it's good to know that your candidate implementations that you're comparing don't necessarily need to be written in the same language or even compiled to the same VM. So you can differential test Solidity against a Python reference implementation or any other language. This is useful for EVM agnostic code like a math library or a Merkle tree library, maybe implementations that are very commonly implemented outside of kind of the Ethereum context. You can also test Solidity against Solidity or any other EVM bytecode compiled piece of code. And this is more useful for rich, stateful, EVM-specific applications. So in practice, if you are deploying a application for production usage in Ethereum, you're probably going to want to test that application behavior more than just the outputs. You'll want to check richer things about the execution like emits, reverts, storage changes, etc. So you can use this tactic for a couple of reasons in the Solidity versus Solidity world. You could also use it to test Solidity against another smart contract language for fun, personal edification, and learning purposes. So specifically differential testing with Foundry, there's a couple of reasons why you want to do this. It's pretty simple. It's just that you can access all the ergonomics of Foundry that Solidity devs are used to having. You can combine differential testing with other testing methods and patterns, be it local testing or fork testing against mainnet, writing explicit inputs, or accessing the Foundry fuzzer. And with Foundry, you can use the cheat code FFI to enable testing with non-EVM implementations. This is basically just a cheat code that lets you run scripts outside of Foundry and access the outputs. It's pretty well documented in the differential testing page in the Foundry book, which is in my references slide at the end of this talk. But today I'm going to focus more on EVM-specific, rich differential testing. So FFI and actually a lot of the examples in the Foundry book right now are a little bit less relevant. For EVM-only implementations, you can stick to all of the native testing patterns of Foundry that people are used to. So there's a lot of reasons why you might want to employ differential testing, but I'm going to go through a couple here, practical examples and their benefits. The first would be for gas optimization. So you could basically, what this looks like is you would write an unoptimized reference implementation in idiomatic Solidity and then rewrite that code into a highly optimized final version, which you would deploy on mainnet. You'd employ differential testing to check that the reference implementation and the final implementation are equivalent. And I call this the Seaport pattern because the team at OpenSea pretty much pioneered this pattern with their work on Seaport. There's a lot of benefits to doing this. Basically, in this pattern, developers can design and build their app more quickly using Solidity. So kind of more intuitive language to get to your final application design and behavior, and then focus on gas optimization later when you've solidified the interface and behavior of the application. At the end of the day, users get a hyper-optimized contract on mainnet, but the reference implementation also becomes a really valuable artifact of this development process. So auditors can use the reference implementation to better understand the expected application behavior. Integrators and developers with less context on advanced Solidity can use your reference implementation to plug into your smart contracts. And even with Seaport, for example, it's become a really valuable teaching tool for developers that are trying to learn inline assembly. People have been studying the reference versus the final to actually learn more about gas optimization. So differential testing these two implementations builds confidence that your optimizations didn't break any of your functionality or expected application behavior. Another really important use case would be for validating upgrades. So you can write mainnet fork tests against your production contracts pre-upgrade and post-upgrade. And differential testing here can build confidence that your new code after the upgrade doesn't interact badly with the state on mainnet. The benefits here are more straightforward. It's, upgrades are sensitive operations, mission critical to be secure. So, having talked about what differential testing is and why we might want to use it for EVM applications, we're going to go through a couple of coding patterns. So the first is what I would call the naive pattern. I think that if most people thought about differential testing on my definition slide, they would probably expect it to look something like this. So we have a single entry point test function, and within that test function, you're basically calling into each implementation, into each reference, collecting the outputs and asserting equality between the outputs. So this might be the most intuitive way you might go about differential testing, but there's a lot of issues with this approach. If you actually try it, it gets clunky very quickly. If you want to make richer assertions about the actual execution of these contracts, such as using cheat codes like VM expect revert or expect emit, then you would need to make those assertions for every single contract call. So you're starting to repeat not just every call, but also every assertion. It becomes a lot of boilerplate, and it's not fun to write. So next, let's look into how Seaport did this. I'm gonna be a little quicker on this, but we can go back if we have time or if people are interested in the question section to get a little deeper into what's going on here. But already you can see this is starting to look cleaner than the naive pattern. You can see that we still have a single entry point test function that is calling both contracts, but it's refactored and changed a bit to be more readable, more usable. So basically they've written their test function. Here it's this dot fulfill advanced order with criteria. And that test function, it looks basically like a normal Foundry test. It has a lot of setup during it, different calls to the target contract, assertions, etc. And what they're doing here is they're just calling that same test function and providing two different target contracts as the context. So here the context struct provides the target contract. Here the consideration is the final and the reference consideration is the reference. And it provides the same arguments to the function. You can also see this wrapper, this test function is kind of a wrapper around it, and we're gonna dig a little bit deeper into that in a second. Something important to note here is that kind of the motivation behind having a single entry point function that calls both contracts is they want to provide the same fuzzed arguments to both test calls. And that's going to be important later. So this might look kind of simple, relatively readable, even though it's a little bit harder to understand than just normal testing that people are used to. It's still pretty nice. But if you sort of start to dig in under the hood, there's a lot going on here that is non-obvious. So Seaport is a very stateful contract, and it was important for these tests to run not only with the same inputs, but also against the same beginning state. And something to note is that this is the default for Foundry tests that are separate tests, right? The setup function runs and sets up the test state, and then every test function runs against that same state. But because in this pattern, you're testing two contracts against, like in the same entry point function, you need to roll back state somehow to be able to run these contracts against the same setup state with the same fuzz arguments. And this is code basically from differential test.sol, which is also in my references slide. But it's kind of hacking around some HEVM weird stuff. Basically, long story short, the HEVM stores assertion failures in contract storage. So if you were to like VM roll back the chain state to try to roll back the state, it would also roll back any test failures. And this is kind of the workarounds that they've come up with to get around that. Okay, so again, cleaner than the naive pattern, less readable than normal tests, but under the hood, the workarounds can be inscrutable for most devs to understand, and that makes this less accessible. So finally, coming to what I would propose as an interesting pattern for differential testing with Foundry. So what you're looking at here should basically look like a normal test, like a normal Foundry test, similar to your existing test suites. You've got the test contract, you've got the target contract that you are trying to test, a setup function which performs some state setup. The only thing to note here is that I've extracted this helper function that deploys the target contract and made it a virtual function. So yeah, your existing test suites probably already look like this. If not, you could refactor them in 10 minutes probably to look like this. So to achieve a differential test, what you would do next is actually just inherit your original test suite, and all you have to do is override your function deploying the target contract to provide the second implementation. So you can see this is like 3-4 lines of code to achieve your full test suite running basically as a differential test. So if you're experienced using Foundry, and particularly the fuzzer, you might have noticed an issue with this suggestion. So with this suggestion, any explicitly defined inputs, anything that the developer writes into the tests will be the same between the tests, like your exact same test code is running. But if you are writing fuzz tests, then by default, the default Foundry configuration, your fuzz inputs will be different between these two test runs. And so to look at whether we can fix this, we're gonna take a side quest into the Foundry fuzzer. So the Foundry fuzzer is basically smart about how it produces inputs to your test contracts. So it doesn't just throw meaningless data at your tests, it's context aware. And the way this is implemented is basically there's a dictionary. It will throw any values from your test setup environment into this dictionary, specifically any values written to storage at any point during the setup, and any values pushed to the stack at any point during setup. It populates this dictionary with these meaningful values, And this dictionary serves as inputs for an algorithm that outputs your test inputs. So because it's context aware, more bugs and edge cases can be caught this way. You can imagine that if you're testing access control on your contract and you have a suite of 10 smart contracts, if you're throwing meaningless data at that access control test, like 0x, 1, 2, 3, ABC, it's easier for that access control to succeed than perhaps having accidentally 2 admin contracts and both of them can call the function. So basically having a context-aware fuzzer can catch edge cases like this more successfully. Something that is important to note is that the algorithm that operates on the dictionary can be made deterministic by providing a salt to it. So if your dictionary is exactly the same and you provide a salt, then your fuzz test inputs are going to be exactly the same. So if you want to make your fuzz inputs the same between these 2 test runs, you can first provide a salt. And then the second thing you need to do is make sure your dictionary is exactly the same. To do this, it's a little bit, it depends on your test setup, right? It depends on the differences between your virtual functions, what you might need to include or exclude to achieve that. So you might probably want to exclude values pushed to the stack. You probably don't need to exclude values from storage if all you're doing in your setup function is deploying a different contract. It's a little bit case dependent. You also want to make sure that wherever you're running this full fuzz test suite, you configure fuzz runs as high as you want it, because the inputs will be exactly the same every time that you run the test. People might be used to their fuzz tests producing different inputs each time they run it. This time it'll be the same every time, so you want to make sure you are throwing enough inputs at it to be satisfied that it might have caught your bugs. So this brings us to a drawback of the proposed pattern. Excluding values from the dictionary makes the fuzzer a little bit dumber, which means it could surface less bugs. But including all the values to the dictionary means that the inputs might no longer be the same between fuzz runs. And that's not actually the end of the world, but it means that these 2 runs don't conform exactly to the true definition of differential testing, which tends to emphasize that you are providing the same inputs to these tests. So to mitigate that, I would just propose you simply run your test suite twice with a different configuration. You run it once excluding dictionary values and once including them. So you kind of get the best of both worlds. You get a broad, meaningful set of inputs checked against your contract, but then you also get like true differential tests. The benefits of this pattern are that it's very readable, it's intuitive, it's quick and easy to try. You can probably take your existing test suites and try this out. If you've been wanting to try optimizing your contracts, you could get started now trying this. It's pretty pragmatic, it's approachable for developers at all levels, and hopefully it could reduce the barrier to entry for trying out differential testing. So yeah, quick acknowledgements. Definitely shout out to emo.eth and Zero Age and the whole team that worked on Seaport. They did really cool work in differential testing that served as a really big reference for this talk. Thanks Evelier for answering questions about the Foundry fuzzer, Presswitch, Jenny Pollack, Aleph for being awesome sounding boards. This slide has a lot of the references that I used when compiling this talk. So if you're interested in digging a little bit deeper, this could be a good resource for you, filtering out some noise and just kind of including a lot of the really core, interesting work being done on this. I'll be posting my slides to my Twitter sometime after this talk, so you can just check there if you want to access the contents of this talk, but also these references for further research. And that's it. Thank you.
Any questions for Anna? Yes.
Do you have any future directions that you'd like to take this project in?
Yeah, absolutely. So I think that some interesting directions. Oh, could I go back to my slides? I think that some interesting directions in the future would be like building directly into Foundry some better syntax and functionality for doing this. I think right now this is not really a first-class citizen in Foundry. If you just look at, first of all, how many people are really using this in production right now, or even for like play use cases. But yeah, something could be really interesting is like building directly into Foundry, checking, for example, asserting that the state root of these contracts is the same after every test run could give you like really high confidence that the state changes between your two implementations are exactly the same. You could even sort of check the entire execution, like trace basically, like the whole call stack, make sure that the inputs and outputs of every call produced by these tests are the same to any external contracts. Yeah, and basically just kind of create richer, deeper functionality for differential testing and maybe some nicer syntax for it. Yeah, everything that we're doing here, we're a little bit hacking around the current constraints of the testing environment, and I think this could be valuable to improve upon.
Anyone else? Yes.
Hey, thanks for the talk. Do you see any downsides to simply testing two targets with the same seed versus differential testing where because you're in the end you're just making sure that you test pass, right? But you won't necessarily check that you exactly return the same values, that your functions might exactly revert the same way. That's all dependent on your tests. Like you're not exactly checking the outputs from your functions. And in that sense, I was also wondering, is there some effort to perhaps have all of this more automated, where you just simply deploy two contracts and Foundry would like automatically look through all the function selectors and just like randomize all of the inputs, and like not you basically having to create these tests yourself?
Yeah, yeah, there's a couple things in there. Definitely great question. So I would say the first thing here, like we're not explicitly cross-referencing inputs. We're running test cases against both. Don't we want to directly cross-reference them, or is it okay to just check the execution? So kind of in the beginning slide was calling out in terms of differential testing, it's not necessarily just checking that functions produce the same outputs, it's checking that all meaningful behavior is equivalent. And in this case, right, like meaningful behavior in the context of EVM applications includes reverts, emits, storage changes, all types of stuff like that. And so these are the types of cases that you're gonna wanna write into your tests, right? Like any normal test, be it unit fuzz, doesn't have to be a differential test. It should check much more meaningful questions about the execution than just the output. It can also check the output. So what you see, for example, here, is that this test is not comparing the contracts, like the test in Seaport. It doesn't compare them directly against each other. It runs a rich test that checks its execution behavior for both of them. And the fact that the execution is the same in that it passes the tests between the both of them basically implies equivalence. But as I was saying before, in terms of future directions, you might want to, yeah, exactly as you said, kind of make it a little bit more automated for the end developer by building syntax for this directly into Foundry. And you could make richer checks like, for example, on the state root being equivalent after the execution of some code, outputs, if you like, being equivalent after the execution of some code, and kind of like free up the developer from having to write this in themselves necessarily. Foundry provides a lot of nice utilities for other forms of testing, so it might want to consider doing it for this. Did that answer your question? Did I not address anything?
No, I think that was good. Thanks.
Okay.
Awesome. Anyone else? Okay. Well, thank you so much for that amazing talk.